Very much. I would also like to thank the organizers for setting up this wonderful event. It's, as always, extremely inspiring to talk to many people around from different backgrounds. I would also like to thank my collaborators on this line of research, so my postdoc Romain Davier and my finishing PhD student Karl Zelle. We are also collaborating with Achim Roche from my department. So let me motivate this line of research actually from a kind of a different direction, which I was recently participating in another KITP program, active matter. So these are systems which consist, very roughly speaking, of many mobile self-propelled agents. So that could be flocking of birds, as you can see here. That could be colonies of bacteria, but also systems of traffic flow are in this range of interest there. So a very loose definition of these systems is that they feature emergent collective behavior, which I guess is nicely illustrated in this flock of birds here, and they have an explicit breaking of detail balance on the microscopic level of description. Yeah? So these self-propelled units. So I want to ask here basically the question whether we can have analogous situations in condensed matter systems. Yeah? I guess we are not lacking collective effects like spontaneous symmetry breaking phenomena. And in this crowd here, we have many specialists that are able to break detail balance, to break equilibrium condition on a microscopic level of description. Conceptually, we are speaking about driven and at the same time open quantum systems. And plenty of examples are here. Prime platform are exciton-polariton systems, which are incoherently and laser-driven, but also systems like this light-induced superconductors or ferromagnets, which were mentioned in this conference, driven magnets, magnonics, nonlinear magnonics. We heard a beautiful talk yesterday about that. Optically driven bilayer systems forming excitons just by optically exciting them or easing the formation of excitons in this way. Or we just heard in the morning by Uncle a very nice talk on quantum materials in optical cavities. Also, Daniele Fausti gave a very inspiring talk earlier this week on experiments. Now, again, can we realize basically active matter scenarios in solid state, or probably modified versions of the kind of traditional one? And then also, how do we have to think, what are the novel states of matter that emerge in this way and phenomena? So here I would like to take a minute to refine this question a little bit. So basically we were thinking about the consequences, or we want to think about the consequences of the microscopic breaking of detail balance. Yeah? So I have a system, say here, a cartoon like at equilibrium, and I perturb it by driving and opening it up at the same time. And then I want to track the effect of this non-equilibrium perturbation from the microscopic to the macroscopic scale. So we want to ask whether there can be universal macroscopic non-equilibrium phenomena, which maybe is not. So we want to go basically to this interesting case, while one should be aware of the fact that most usually, even if you break a little bit the equilibrium condition at the macroscopic distance, this perturbation is irrelevant. Just think of this table of light, of matter with a little light shining on, and of course that's an irrelevant perturbation, but I want to argue for the circumstance in which this could be interesting. Now to ground this, so there's a nice working example. So exciton-polariton driven condensats, they map to the so-called Cardar-Parisi-Cheng, a universality class, the dynamics of the Goldstone mode of the phase, and in fact this was observed just 2 years ago by the group of Jacqueline Bloch. So if you want to conceptualize this, so take an equilibrium system, or make it concrete in an example, take an equilibrium atomic BEC and compare it to the polariton BEC. Both of them show a condensation phenomenon. In that naive sense, it's a similar state of matter. But if you look at the macroscopic behavior of the correlation function, the long-distance behavior, then you will actually indeed see differences in that this polariton system is in that class of problems here. So how can we approach this system or this set of problems? So we want to describe ultimately the systems which are microscopically described by electrons, spin, and lattice. So what you have in a piece of condensed matter. We should have some knowledge about the symmetries of this problem, and we should make, for example, here I list the systems, what kind of continuous internal symmetries they can have, but we will also in this talk touch about continuous external symmetries, time translations, space translations. And the second ingredient is we want to break detail balance on this microscopic level. Then we can do a kind of a coarse graining procedure that is basically solving the problem for the ordering pattern that it wants to develop. So we want to determine what is the basic collective effect in this problem, and we have to have knowledge about the symmetry breaking pattern that emerges in this system. So in that circumstance, we can formulate a non-equilibrium order parameter Landau type field theory for the problem. And then in this, then you run down even further, or run up, basically go to larger and larger distances, incorporate the fluctuation effects, and then characterize this non-equilibrium state of matter, and you can see if it compares to an equilibrium system or not. So the degrees of freedom that are remaining in this regime are the soft modes, in an ordered state, some Goldstone modes, critical degrees of freedom, things like that. Now in this talk I want to introduce an overarching kind of theory of this type on this mesoscopic level. I will then point out what hopefully interesting phenomena occur, and basically only in the last step connect back to some experimental platform. So that's the logic, and I stress here again that the input for these theories is pretty minimal. So we need this breaking of equilibrium condition in a driven open system. We want to have a continuous symmetry which can get broken. It can be an internal or an external symmetry. And the reason why this concept can still be predictive is simply the very concept of universality that we see a lot in nature. So the dominance of the collective long wavelength fluctuations, this holds in or out of equilibrium, doesn't matter. The question we want to ask is really, so is there a difference in this universality mattering depending on whether we have equilibrium or not on the microscopic scale? So in this talk, I want to point out that this can lead to novel types of phase transitions, universality classes which are not smoothly connected to equilibrium universality classes. Also, I want to characterize a few examples of non-equilibrium states of matter with long-distance correlations without equilibrium counterpart. And I will ground this in a few platforms, ferrimagnets, exciton, polariton, magnon condensates, many more inspired from this conference. Okay, so then let's go with the description of these systems on the mesoscopic scale. So this is the order parameter theory, how you should think about that. Formally, this is the equation of motion for a relativistic ON model with an n component vector that can describe a bunch of symmetry groups that we have in these systems. Of course, for example, this term, this inertial second order derivative, is the one of a harmonic oscillator, or what you see in the nonlinear phononics and magnonics that we've heard about. And then this problem has an ordinary phi-4 potential. So this is the gap parameter. This is the nonlinearity with this rho defined in this way here. Now let's add a bit of complexity, which is necessary. We need to be able to account for dissipation, for these mesoscopically fluctuating degrees of freedom. And if we would forget about the second order derivative, then the problem I'm writing here is including the stochastic noise that you need in order to compensate the fluctuation that compensates for the dissipation. then without this term here, that would be model A of Halperin and Hohenberg developed to describe dynamical critical behavior at equilibrium. And now I said we want to break the condition, we want to track the fact that equilibrium is broken on the microscopic scale. So you can then convince yourself that if you write these two terms here, they violate formally the condition of equilibrium. In a way of saying this is they break a symmetry that is associated to the presence of detailed balance of the state. So these are our non-equilibrium perturbations, if you like. You see that this, or you can convince yourself that this model has actually two relevant parameters. So one of them is this usual mass or gap term. If you tune this from positive to negative, then we are actually going from this kind of parabolic potential to this sombrero potential here. That would trigger the usual equilibrium ON transition. But there is a second relevant parameter in this model, which is the basically loss, so the damping in this problem. And this becomes interesting when kind of think of an incoherent pump and an incoherent loss. If we pump it too hard incoherently, then damping turns into anti-damping. This parameter here goes negative. And as we will see, this is a very simple instance of triggering a time crystal or a limit cycle. Yes.
If I make that negative, so you also have relations on the correlation function for C. Do I have to make that negative as well? How do I do that?
It's a very good point. Yeah. So formally, I can do this at equilibrium, but very similar to tuning this R negative, I need a nonlinearity to compensate for that. Mm-hmm. Similar role is taken now by this non-equilibrium term, which basically is the analog of this effect. The nonlinearity stabilizes this. It's the same in exciton polaritons. You have a two-body loss that stabilizes, that basically makes you find a new minimum. Mm. Yeah.
You don't need the damping to have the you don't need damping to have the non-conservative forces.
That's right, but I would, if you look at it in terms of, so to say, single particle processes, two particle processes, so that the single particle process typically dominates, and then there's a two particle process, so formally you're right, but technically, in a physical system, at this mesoscopic scale of description, you would always have this. So, in fact, it's the interesting question then how to tune this negative, how to make it an anti-damping. But let's, at the moment, just so to say, go through this problem here. So let's do something very simple to begin with. Yeah? So we look at the strip of all the complexity. Yeah? So let's forget about the spatial gradients here. Let's forget about the noise. Let's do a simple mean field theory to begin with. Yeah? So if we have R positive, parabolic potential, and a positive damping, then the system is disordered here. If we go to negative R's, so then we have the usual spontaneous symmetry breaking of an ON model. So this the vector here will point then in some direction, will order in some direction for n equals 3 on a sphere. And if you go to this negative values of gamma to anti-damping, then in this model you will actually initiate a rotation of this order parameter. Yeah? So instead of being statically ordered somewhere, the system goes on to a limit cycle behavior. So in fact, this limit cycle can come in two flavors, which we'll encounter later on, depending on the sign of the difference of u and u prime parameters here. So we can have for this parameter negative here, we have something like the analog of a van der Pol oscillating phase, so that for n equals 1, this, and no spatial degrees of freedom, this is the van der Pol equation here. And as I was already mentioning, the other possibility for the other sign, we get this rotating solution. And then you can ask, so what's the, for example, Goldstone mode sitting on top of this? So you spontaneously pick an axis, or you spontaneously pick an orbit. Now let's zoom into, let's do the kind of full analysis, go beyond this mean field approximation and ask about the nature of all these phase transitions connecting these different phases. So now we really need to do this coarse graining up to the macroscopic distances, for example, by following an RG flow for the model. Now this, basically what I was selling as the ordinary boring phase transition, in fact, has this phenomenon that I was mentioned, emergent equilibrium behavior. So despite the fact that we perturb the system out of equilibrium on the or microscopic scale, so at long wavelengths, the universality class is one of the equilibrium classes which are known since the 70s. Now this transition here is already a slightly more interesting. So it's an order-to-order transition which goes through a critical exceptional point. And when you look into this problem really in more detail, then you find there's a kind of fluctuation catastrophe which gives you a weakly first-order fluctuation-induced phase transition. The most interesting to my taste is still this kind of phase transition, which I want to discuss in a bit more direct, in more detail, which means the direct onset of a time crystalline of a limit cycle phase starting from a disordered one. So this gives you a new universality class, which is to be really distinguished quantitatively in its critical exponents from that one. So let's discuss this problem in a bit more detail here. And there's an interesting phenomenon going on that one should really keep in mind for all these kinds of problems here. So it's a transition which goes via a critical point where there's still a finite frequency scale alive. So when we tune from damping to anti-damping up to a small renormalization correction, so really the gamma effective, the effective damping rate goes through zero at this transition point. So this means that if I plot the envelope of a typical field configuration that I have to sum over to evaluate the partition sum, basically, or the dynamical partition sum for this problem, then it will have an envelope, typical field configuration, which has a timescale 1 over gamma, and this diverges even at the transition. Conversely, as you can literally see here, there's still this finite frequency scale in the game, and that gives you basically a very short time oscillation of this field configuration. So the actual one has this internal structure. So if I take this and write, just parameterize the typical field configuration here, then I should decompose it into sine and cosine with slow envelope functions chi1 and chi2. These are my slow degrees of freedom, and then I can determine the symmetries of those in a kind of, you can do it practically in rotating wave, or you just base it on symmetry. So, of course, this ON symmetry is inherited by both this slow chi1, chi2, so they result from this ON symmetric variable. But also, the time translation, which is just shifting time a little bit, it has a gigantic effect on this inner oscillating functions. But they have basically no effect on this slowly varying functions. So time translations basically act as a rotation in this inner degrees of freedom, which come about because the system is driven through this critical point. So upshot of this consideration, the right symmetry group to study the critical behavior of this direct transition onset of a time crystal is not just ON. We have to basically look at ON cross SO2, which is this emergent internal symmetry. Yeah.
So I'm just wondering, what physical system, I have to admit I'm a little bit lost, like, I understand the math, but what actually considering, like, an example of this?
Example would be a beautiful example, this nonlinear phononics. So they realize this inertial time derivative.
So what's phi?
The phi would be basically the phonon oscillation amplitude.
And you don't resolve spatial degrees of freedom, it's only time?
Of course, no. I mean, this is also everything in space. So slowly varying fields in space.
So I see, you drive a crystal and you see it.
Yeah, exactly. For example.
So question, so is it related to a synchronization transition like in the Kuramoto model, like in space?
Yes, yeah. So that is a picture. So if you have a pattern that forms in space, that also leads to such an enhancement, basically because you have a scale that developed, that you have in space. There's some wave factor Q0, around which describes the periodicity of the spatial pattern that also leads to such a kind of enhancement of the symmetry, which is actually a very interesting point. If you perturb such a system slightly out of it, it will also respond strongly.
Thank you.
Yes.
Would a laser, the onset of lasing, fall into, where would that sit in sort of your picture?
That's another example. Yeah? So you can look at so a lasing, yeah? You have a complex degree of freedom. So if you write it in terms of x and p, yeah? So basically it's switching between Lagrange and Hamilton formulations. Yeah? So you have a first order Schrödinger type evolution for the complex amplitude of the problem. Equivalently, you can write it in oscillator x and p coordinates, and then you eliminate the p coordinate, if you can, so details, but then you get, again, also something like a second order time derivative. So indeed, I mean, these exciton polariton systems, they are precisely also, I mean, in a pretty, maybe it's not so interesting physics-wise, this precise effect, but you could think of them also, the condensation in exciton polaritons, as a simultaneous breaking of the U1 phase rotation symmetry and the time translation symmetry. Yeah? And this is an observable effect. Yeah, you can see if you look at the G1 in time function, there's a rapid oscillation. That's basically this inner structure that you see. Yeah? So the point I wanted to make, I mean, that's not ideal when the model is too far from something concrete, but the point is, of course, yeah, so that this is a model that I want to later on connect to kind of concrete platforms. Yeah? So, but one can use this to understand the basic physics of these non-equilibrium systems. Okay, so let's then write down the most general, we can use again symmetry, field theory or stochastic equation of motion equivalent to a field theory, which is for the group ON cross SO2. Yeah? And in fact, this theory here also can describe both these oscillating and rotating phases here. And we can also ask this theory to be in or out of equilibrium, again, based on this thermal symmetry. Yeah? And a system at equilibrium will have the circumstance that this dissipative evolution and the reversible evolution, yeah, they are basically aligned in this way. The coupling constants, these two H, C, and D, are proportional to each other, while an out of equilibrium system, there's no relation between the dissipative dynamics and the reversible dynamics acting on it, and that would look like a spread situation. So this is our friend. This is what we want to analyze. Yeah? So a non-equilibrium variant version of this ON cross SO2 symmetry. So, and then we ask basically if we can't drive it super hard, yeah, so what happens if we have this slightly, yeah, so slightly spread situation, or close to this, but not quite. So, and then we did a renormalization analysis for this problem here, and for any n larger equal 2, we find actually that indeed there's a new non-equilibrium universality class, which I will go through here. So you can think of this problem here in terms of a parameter space where I have some surface in it where equilibrium conditions are valid, are realized. So this is the equilibrium surface, and there is also a critical point, a Wilson-Fisher interacting fixed point for this problem, which was even for ON cross OM determined earlier on. But what we then find, yeah, out of this plane, so far from equilibrium, there sits actually a complex conjugated pair of new fixed points, which are characterized by exponents which are manifestly different from those of the equilibrium model. So this means we found a new universality class. And there's also an interesting kind of scenario of a, if you wish, spontaneous breaking of equilibrium conditions in the following sense. Think I initialize, or I put my system on the microscopic scale very close to equilibrium, but not exactly. Yeah? And then I track the RG flow, and it will be activated to flow to this new fixed point. Yeah? So this means actually even a weak drive out of equilibrium in this circumstance gives you a really commuting limit, and you will see on the asymptotic scales this new universal behavior. Of course, the caveat is if you only put it slightly out of equilibrium, the scale where you can observe this might be very large. But conceptually, it's interesting to note that for models in this class, the equilibrium statistical mechanics is at stake. So if you have such a system with this group, such a material, and you shine some light on it, so then you will really flow away from this equilibrium, and you will find a behavior that is very different, and that comes back, for example, a system with a spatial pattern, with an ON symmetry, and the spatial pattern also falls in this class, and will be very, very susceptible to being driven by a tiny amount of out of equilibrium. For example, frustrated magnets are an example here. Now, how would we can see this critical behavior here in a, at the moment, thought experiment? So it will be showing up by a violation of fluctuation-dissipation relation. So remember, at global thermal equilibrium, one way of thinking about it is that all subparts are in equilibrium with each other. So no matter which subpart I look at, if I trace out the rest, I will find temperature T for this remaining subsystem. This is equilibrium, and in an RG language, this means that temperature is scale invariant. So if I integrate out this subsystem shell here, then the remaining system will again sit at temperature T, same temperature. But if I have a system out of equilibrium, this is violated. Subsystems are not in detail balance with each other, so temperature will become scale dependent in general. And we find here, you can still define a relation of fluctuation and dissipation with respect to each other, defining an effective temperature. But this now depends on scale and will actually universally diverge with one of these exponents that we determined. And this is, if you can determine the temperature in a frequency or momentum resolved way, for example, by taking these Stokes, anti-Stokes peaks, then you could see this universal phenomenon. Okay, as a second part, I would like to discuss time crystals. So given systems that only have maybe a Z2 internal symmetry, nothing fancy, but a time translation symmetry. Yes? Yeah. Yeah.
Hi. Before you continue, just a question for the motivation that you did in the very beginning with the active matter. Mm-hmm. Can you maybe draw the analogy overarchingly to what you introduced in the beginning? Because active matter, I usually understood it basically like a combination of individual actors that are individually driven, and just basically by the behavior with respect to the neighbors form something bigger. So what would be kind of the analogy in the theory you presented? What would be the individual actors, so to speak, and what would be their drive?
I think that the real connecting point is that it doesn't matter how you break exactly the equilibrium condition. It can be that these things are self-propelled entities or so, or it can be that you drive a system with a laser, and you open it up to a reservoir of degrees of freedom. You think about this problem on these intermediate scale distances. Both these problems will be described by an effective order parameter field theory, which violates the detailed balance. So we don't care too much about the precise mechanism of breaking. We can,
Okay, but basically you're for now ignoring the microscopy of this, how it comes into play, basically. But in principle, if you would find a physical system, to get the parameters that you put into your model, you would need to extract them still microscopically.
Right. I mean, so the ideal situation is this. I give you a system maybe in a cavity, driven cavity. I calculate the parameters of this effective mesoscopic theory, understanding what the order parameter is. And then I use this approach and coarse grain to the asymptotic distances. So then I will find the long-range correlations and so on.
Okay, thanks. Yeah.
Okay. So let's think about this time translation symmetry breaking and its Goldstone modes. So usually symmetry breaking is just, one way of diagnosing it is to look at this 2-point correlation function, saturates as a function of large distance to a constant because the system has ordered in this way. Now, time translation symmetry breaking can be defined in the exact same way, just that this parameter here depends on time because this field orders in a limit cycle in a time crystal in a time-dependent periodic way. So the setting for this problem is, as in our example, the equation of motion should be time translation invariant. The parameters don't explicitly depend on time. But then the solution of this equation of motion breaks time translations because it's oscillating. So as we've seen, these limit cycle solutions. And then Goldstone theorem tells you that every spontaneously broken continuous symmetry has to come with some soft mode. In the case of continuous time translations, this formally can be expressed if this function here is a limit cycle solution, then also the shifted function is a solution. So this T0 gives us a manifold of parameters which are equivalent stable states in the system, parameterized by T0. And then this Goldstone mode construction means just promote this generator of the manifold to a time and space.
Can I ask you? Okay, this is a very naive question. I mean, if I take any system and I assume we are in the nonlinear regime, Chi3, Chi4, and then I just bring the system out of equilibrium, this response function automatically breaks time reversal, time translational symmetry.
The response function, so you're saying...
I'm saying that the system automatically breaks time
but spontaneously or explicitly?
Anytime.
So is it because an explicit...
I never understood this argument of the time translationally breaking symmetry because it's broken anyhow.
Right. Let's think about it in the following way. On the microscopic scale, if I have a driven system, for example, I drive it with a laser. Of course, this is a breaking, explicit breaking of time translations. Then, however, I coarse grain this problem to this mesoscopic scale, and it will be described, for example, by a Lindblad master equation with time-independent parameters. Right? This model is, so to say, the starting point for this analysis. So this model, at this mesoscopic level of description, I've averaged over time's scale such that the parameters look effectively time-independent, and then the system can make a decision whether the solution of this problem has an explicit time dependence or not. So in this way, that's how I'm thinking about it. You can, of course, connecting micro and macro, you can think about it microscopically. I drive it, and this driving just shows up as a very, very different scale. So you have a very fast driving, but it shows up as a slow rotation of the order parameter. So in this way, there is a logical connection between these phenomena.
What I was thinking is, if you have a slightly infinitesimal perturbation, that you do it randomly in time.
Right.
And then you look for the time evolution, that system will have a time translation symmetry broken.
If you average then over this macroscopic time scales, then it might look time independent. So this is the how you derive a Lindbladian. So you have a small Okay, but
Sebastian, before you continue, I think the definition of a time crystal is more or less on the slide, but can you just remind everybody in the room what is your definition of a time crystal?
Right. I mean, we've seen these. I've shown you this rotating and oscillating order parameters. So this is basically the feed. So this is the reason why looking at this correlation function, because the order parameter oscillates, the solution of the equation of motion oscillates. Therefore, so we can have an ordering of this type. So I think it's basically just replace the usual condensation, which is static. So this was the order parameter pointing somewhere, by an order parameter that now rotates. So this is the definition.
But it rotates at a different, there must be a driving frequency in there. The way I understood, for example, Floquet time crystals was that there's a drive frequency and you get a subharmonic instead of just higher harmonic.
That's true. That's a spontaneous breaking of a discrete time translation symmetry. Here we are speaking about systems. The equation, the stochastic equation of motion or Lindblad or what, is really continuously time translation invariant. And that's somehow more interesting because then because continuous time translation.
It's a continuous driven dissipative time crystal.
Exactly. Continuous, totally Yes, the most generic thing. So still, it's spontaneously the system starts to rotate. Okay, so let's look at this van der Pol, simple most example, n equals 1 of these models. So this is the equation of motion. It's nonlinear, it's stochastic, it has space, degrees of freedom. It just has a discrete Z2 symmetry, nothing continuous on that level. But we do this Goldstone mode construction. It's really a geometric construction incorporating basically some limit cycle solution, parameterizing this in the proper way here. And then we find this Goldstone mode dynamics. If you like, you can call it a chronon, because it's really like the phonon of broken space translations. This is the equation of motion that we can systematically compute, so we can get these values here from this equation. And then you can see, so first observation, so according to this spontaneous symmetry breaking, the limit cycle naturally hosts gapless excitations. The mechanism needs no continuous internal symmetry, only external time translation symmetry. And in particular, you notice this Goldstone mode is nonlinear here. And this nonlinearity, again, going through it from equilibrium or not, is forbidden in an equilibrium system, but on the other hand, is equivalent, or makes this problem here, connects it to the famous Kada-Paresi-Sang equation. So just a word on this equation. It was described originally to describe how an interface roughens. So here, a growing height by depositing particles from above, operated under non-equilibrium condition on a tilted plane in a gravitational field. Why is this equation important and famous? Because indeed, this parameter lambda measures the breaking of equilibrium condition. And we also have here a situation now in low dimension that a small perturbation out of equilibrium gives a giant effect on the macroscopic distances, because the system reaches a new fixed point which is deeply out of equilibrium. And there's multiple active matter contexts where this equation is relevant. For example, also quantitatively defect growth in liquid crystals as a platform. And recently, replacing the interface by a phase variable of the exciton-polariton condensate. This is also has been seen, this scaling behavior by where the drive is a laser. Yes.
This might be a silly question, but are we at equilibrium? Because we have driving.
Sorry?
So are we at equilibrium? Because we have driving.
We are not at equilibrium. We are expressly not at equilibrium. This is not the notion of equilibrium as non-equilibrium as something that evolves in time. It's the notion of a flux equilibrium state.
So why are you so concerned about equilibrium?
Well, I'm taking it basically as the reference, and I want to see if we can have something different. So the whole goal is really, making it sharp. In which kinds do we get new states of matter? The way of thinking about it is via this long-distance correlation functions. So we are all used to this. Okay, and there's also other realizations in ultra-cold atoms and NISC devices. I mentioned that 2D realizations are completely outstanding of this problem. Now, let's look at this numerically. So I did this Goldstone mode construction. If you don't buy it, then you can rely on this numeric. So we start from this van der Pol field theory and we solve it numerically. And you can see, indeed, this envelope decay behavior that I was mentioning. You can see the KPZ exponent in 1 dimension, in 2 dimension. So I think this is really a very robust, time translation symmetry protected realization of KPZ dynamics that works in any dimension. So we are currently exploring Josephson junction arrays as a platform, but it was also very inspiring to hear the talks about this nonlinear phononics and magnonics, which are really exactly in this ballpark. So this works that have been discussed. One thing that is really different from the standard KPZ is that this limit cycle variable is periodic. So something repeats in time. So that means this theta here is really like a phase variable, a compact variable, and that you should think that that allows for vortex defects to form. For example, in 1+1 dimension, 1 time, 1 space, if you look at the problem in the right way, you can see these space-time vortices. So in a plane of x and t, there's a phase singularity that you can define here. And for example, in 2+1 dimension, we see These vortices are more purely spatial degrees of freedom, and they have also the impact on in certain parameter regimes on the long distance correlation functions. This I'll drop it. And an outlook of this is that we looked at only n equals 1, the pure time translation Goldstone mode. But think that we can also look at this n larger equals 2. That makes us study nonlinear sigma models in this out of equilibrium. For example, this oscillating phase here has a different symmetry breaking pattern than the rotating phase. Yeah? So these are two different, if you wish, mathematically cosets on which the dynamics of the Goldstone modes happens. And it's preliminary, but these problems here, this problem maps to a known problem, while this problem for the rotating phase is to, I understand, new. And one beautiful application of this would be dynamical excitons with a valid degree of freedom with a bigger symmetry group as U2 times U1, which is very close, I mean, to O3 cross SO2. So I guess it's really the tip of the iceberg with this KPZ, and there's a lot of room to find new physics. So maybe as a last brief point,
Sebastian, probably very naive, but let's say in the period doubling case, so there you break discrete time translations. So then you have gapped phonons.
Right, I think that's...
What are they?
I guess they would then not determine, so give you anything interesting in the long distance correlations. It's like, I mean, in the Ising model, if you think of usual, I mean, internal symmetries, there's no gapless mode in the broken phase of an Ising model. That's analogous.
But you can excite them. Is there a sense of exciting these models?
I think we can discuss that, but in the spirit of, can we identify some Goldstone mode? Yeah? So I think you need the continuous aspect of the problem. Yeah? It's crucial.
Yeah. So could you provide like one example of, I mean, not Goldstone modes or some fancy, but just of a phase that you call a time crystal? Like, give me one example. What is that?
Most simple example is an exciton polariton condensate. Yeah?
And so what's the time crystal there? I'm sorry.
The time crystal is just the fact, and it's between deep and trivial, so that an out of equilibrium condensate. Yeah, so the time translation symmetry is broken. There is basically a kind of chemical potential emergent, if you want, so that the phase of the condensate rotates all the time. That's different from an equilibrium BEC, where you would see no quick rotation. Yeah? So you can do the G1 as a function of time experiment in exciton polariton condensates. You will see a rapid oscillation. This is the most trivial. But conceptually, if you're asking for that example of a time crystal, while if you do the same G1 of T in a Bose condensate at equilibrium, you see no fast oscillation in this problem. So this is an example. And also, I mean, we've seen the talk by Ahana Chakraborty. She was reporting on these kind of limit cycles in the phononics. So these are systems which are not, there's not a complex variable that can rotate. There's rather the second time derivative term, so that's just the oscillating of the phonons.
But it's not like a harmonic oscillator, you call it time crystal.
No, you need, of course. That's why I'm putting the definition with x going to infinity. So as in spontaneous symmetry breaking, you want a collective effect, and then this is a, so to say, line 1. Of this problem, collective effect, macroscopic condensation phenomenon.
Just a clarifying question. To call it a time crystal, we should also take it to time to infinity, right? So those oscillations should survive.
They persist. So it's this is only possible in a driven system. So that a rapid scale develops spontaneously in the stationary state. So you let it evolve for infinite time, and then you still see some observables which oscillate. That's impossible at equilibrium. You could otherwise construct a perpetuum mobile.
Yeah, and in numerics that you showed, the envelope was decaying, but I suppose it's not decaying to zero.
So this is the relative time between two points. A relative, so I take here time 0, and then I probe it autocorrelation function at a later time, and then you see the rapid oscillations, and all over expected from physics, it has to decay somehow.
Can you map Can you map what you're talking about onto like Rayleigh-Benard convection?
This is a related problem. I think it doesn't have necessarily this. This is, I mean, a nice example, yeah, of this. I mean, this was analyzed by John Toner. I think that also has connections to KPZ, in fact. Yeah? So this Rayleigh-Benard. Yeah? So it's another example of this strong universality. Yeah? So that a very different, there's a convection of clouds or something like that might have similar long distance behavior. The question is, of course, how to probe this in such a system. Yeah? In these systems, I guess you have much more tools to probe these things in practice. Mm-hmm.
I'm wondering if maybe it's worthwhile to look for eigenmodes with complex frequencies or energies. In analog, there's been a lot of work in time-dependent media, famously by I think Nader and Guetta, to show that you have instead of exponentially decaying states into the gap. Once you have a gap, you have exponentially growing states.
Yeah. So, you mean this stuff by Andrea Alou and
yes,
this
also.
kind of
Yeah.
No, they are also very. I mean, all these systems are non-Hermitian, if you like. They have two features which I didn't see so clearly in this line of experiments that you're mentioning there. You want to have some nonlinearity. Yeah? So that is basically all nonlinear fluctuation effects, and you want to have, in fact, a mesoscopic system which still has some noise. Yeah? So these systems are often very, very well described by deterministic non-Hermitian dynamics. Here we want the combination of fluctuations, mesoscopic, so small systems, and nonlinearity.
So the point is exactly that. If you have any degree of noise and you have any exponentially growing states, those dominate the behavior of the system.
Yes.
So.
Mm-hmm. Yeah, I mean, this is, you can look at it, this is kind of the growing interface in the KPZ. Yeah? So I mean, it can be the phase that rotates all the time. It can be something that grows at infinity. So all these are growth phenomena, and they fall in this class. I agree. Mm-hmm.
Just to understand. You should have a time scale that this non-equilibrium stationary state you get even in this non-equilibrium quasi-state survives, because I think your order parameter is nice, but has to have a lifetime.
Mm-hmm. The lifetime is basically, I mean, this is gamma parameter. Yeah? It can be a fixed number. Yeah? So basically, if you could think about it like that, if I push the system in an unordered state, then it has to react to this, like in a laser. Yeah? So in a laser, which you pump stronger, then you lose particles. Yeah? So then, I mean, you have all the time a finite anti-damping. And what does the system do with that? Well, it stabilizes in some non-trivial laser minimum, if you like. Eh? So I would say these systems, they have finite lifetimes all the time, but you also, so this is the single particle loss, but they also have an incoherent single particle pump, and they have maybe even something like a nonlinear loss. Yeah? So in the exciton polarity, a two-body loss, something like that.
Yeah, but I was thinking more if you have two order parameters.
Yeah. Mm-hmm.
Like if you have superconductivity with charge density wave or any other thing.
Yes.
And you have losses, the two are coupled.
Yeah.
Could you drive them that they are coupled in a constructed interference state that gives you something?
That is, of course, super interesting. Yeah? I mean, so basically thinking about the possible order parameter theories, incorporating competing orders in this way is a possibility. I think one has to understand the rough, maybe on the mean field physics level, what's going on, and then you can push it through this machinery to see what comes out. Yeah.
So let me suppress the questions and please go on.
I go on. How much do I have? Minus 3 minutes? Or? Yeah. Okay. Just accelerating. So just two strategies how you can get there. Yeah? Strategy number one, start from an ON model and drive it hard. Yeah? So let's take a ferri magnet, which has the group O2, which is rotations and some reflections. And this, if you do it at equilibrium, you lower temperature from a paramagnet into a ferro or antiferromagnet, and then into this ferri magnet where a Z magnetization sticks out of the Z plane. Now this phase diagram, now you drive it really hard, for example, by a terahertz magnetic field, Yeah? And then we basically find this full phase diagram realized here. So for example, this ferri magnet at a weak drive, yeah, so the Goldstone mode is easy to access, to get going, yeah, and the ferri magnet would start to rotate. So this is another example of a limit cycle that you can induce by a very weak drive, close to equilibrium down here. Now this first order fluctuation induced transition, yeah, so that is this line shows up here, and this is a rotating ferri magnet, a static XY magnet, and this line here, so you see you have to really drive it hard, would realize this emergent symmetry and the novel universality class. So this model here basically has all the phases that so a ferri magnet is a concrete example which would realize this. Another strategy, right away start from this funny symmetry group here and break the equilibrium just a little bit and then rely on the RG will do the job of generating the non-equilibrium state by itself, by the spontaneous symmetry breaking of equilibrium, if you like. So we break equilibrium by, for example, lossy and incoherently pumped systems, as we said, and the ingredients to realize this is basically you need two complex order parameters. That's a bit what Angel was asking. So two complex order parameters and an exchange symmetry between the two. This realizes precisely this group. And for example, exciton polaritons with a polarization degree of freedom where the SU2 symmetry is broken, right away, it's like a bit the ferri magnet example, yeah, is right away broken to this down here. Or magnon condensates with this YIG material, which has a very weak damping, I understand, also offers the possibility of having Bose condensation in two degenerate minima, which would also realize this exchange symmetry. So, and in this conference, or in the program more generally, I got gigantic inspirations, yeah, so of many, many platforms that I would like to really look at from this point of view. Okay, with this, I stop and thank you very much for your attention and all.
Thank you very much. So maybe one or two questions? Short questions? No? Is it okay? Yeah, okay. So let's move to the next talk. So thank you very much.